announce the first speaker of the BPM seminar day, Hils of the University of Münster. And he will talk about Lang-Weil type point estimates in finite difference fields.
Thank you very much for the invitation. It's a pleasure to be here again. And thanks for all of you who come early in the morning. Well, so early. So I will talk about joint work with Dor and Hrushovski. Here, Vincent, and Tinjan Zhu. The paper is on archive since this year. So I'm sorry, some of you have already heard a version of this talk. So it has a little bit evolved since. Hopefully, so what is the plan of the talk? So, in the first part, we will talk about the rank estimate and point counting. Then about coarse dimension. This is a notion in pseudo-finite structures, coarse dimension in pseudo-finite difference fields. And then we will do some difference algebraic geometry, but not difficult. And Frobenius specializations, by which we mean if you have a difference variety over a field of characteristic P, so you have a field of characteristic P and an automorphism sigma, and you have sigma equations. You may also replace sigma by the Frobenius map, and then you get an algebraic variety. And this is a process one has to understand in this business. And last, this is maybe the main monotheoretic ingredient at the end. So valid fields is an automorphism, so valid difference fields, the monotheory. And the proof sketch of the estimate result. Oh, so that's the plan. So, since this is a talk with I don't know, 80 minutes, questions are even more welcome than normal. We have time. Okay. So let's start with. I mean, we all know the Lang-Weil estimate, but the only thing we're interested in is let me call this strong form of Lang-Weil, because we want a control on the constant. So you know, Lang-Weil estimate, there is a constant. So we call this from Lang-Weil. In this form, due to some computer scientists, Carrefour and Matera. So, what do we need? I mean, so let's say dd will be the dimension, and L will be the degree of the variety in question. For numbers, there is a constant depending on L and D. Such that blah blah blah. So in every finite field, okay, do it. But the important thing is depending polynomially on L. So the constant will depend polynomially on the degree. Such that, and now the usual thing, if V is an algebraic variety absolutely reducible algebraic variety defined over a finite field Fq, of degree bounded by L, then we have the end of dimension D. Then we have the very well-known point count estimate, which comes for curves from the Riemann hypothesis for curves over finite fields. So the cardinality of the set of rational points is right. It is roughly what it would be if it were an affine linear subspace. So it's due to the D, and then the error term is the constant due to the D minus 1/2. But the important thing, as I said, this is the classical Lang-Weil, but the thing I insist on is we have a polynomial dependency on the degree. That's the only thing. So we need this, and you can already see if you want to reduce questions about difference varieties and you plug in Frobenius, the degree explodes because you plug in for difference polynomials, x becomes x to the q. So obviously the degree will explode. So usual bounds will not work, but this polynomial dependency will be good enough later to use such a result for difference varieties in a uniform way when Frobenius can be. So here we don't need any sophisticated notion of degree. Enough to know and that's the only property we will need, that if V is given by as a zero set of polynomials, say 1 up to Fn, then the degree is is at most the product of the degrees of the Fi's. So a very naive notion of degree would also do. Here the degree is the total degree as a polynomial in several variables. So that's the only thing I will use. So, okay. So this is for algebraic varieties. Now we are interested in analogs for difference varieties. So when we have a symbol for an automorphism. And here these are polynomial equations, uniform answers on number of polynomial equations. But what about adding a symbol for the Frobenius in this setting? So we are interested in, weak, of course. We will not have such a strong result. Weak analog for difference varieties. So as you know, the term difference comes from the automorphism, for example, of C of t, sending t to t plus 1, and then you have an algebraic equation, then a difference equation. You can see there's an equation with the automorphism sigma. That's why that's the reason for the word difference. So difference varieties. What does it mean? We work in the language L sigma, which will be the language of rings, but we add a unary function symbol to be interpreted by an automorphism of the field. And polynomial equations are replaced by sigma polynomial equations, where now the polynomial is an element of k of x sigma, where if k sigma is a difference field, or field with an automorphism, x is x1 up to xn, then k of x sigma is just, it's a free object on n elements for as a difference algebra, but that just means you take the polynomial ring, but then you formally add variables for iterates under so there's a natural action of sigma on it. Good. So we are in the most of the time, or almost always, we assume that the difference field is inversive. Usually people define, or sometimes people define difference fields as a field together with a distinguished endomorphism. Now I want an automorphism, i.e. sigma is not just a field endomorphism, but it's an automorphism.
But sorry, but on the polynomial ring, you don't have
not
sigma minus
exactly.
one.
I don't have sigma minus 1 and I don't want to add it there. Exactly. So there is sometimes also we will see later the different function field of a difference variety. I don't want to take inverses, but most of the time we will close off under inverses as well. It's a little bit like in this story also, of course, the map x sent to x to the one to the pth root of x in characteristic p is something you don't add to the language. But of course it is around, and it's quantified, in every field of characteristic P, which is perfectly defined the bijection, and we will later have to do this yoga also, not just for P and for sigma. So like a very general notion of a rational map will be one, you can invert sigma, you can invert P. Okay. Good. What are the finite difference fields? We need a notation. Notation for finite difference fields. So P prime two natural numbers. All difference fields, all finite difference fields are of the following form. Exactly one by difference field associated to the prime P. I don't know whether in this direction I do it M and N or N and M. Let's see how to do it. N and N. So we just take the field with P to the N elements and with the Frobenius P to the N. Of course, this is exactly, since we know the automorphism group of Fp to the N is just given by the maps Frobenius P to the N for N less than N. These are all finite difference fields up to isomorphism. All up to iso. Okay, I enumerate them for the whole talk. Pf of Pi, Ni, Mi. Just an enumeration of this is the finite world, and these are the objects we want to interpret different varieties in, take points, sets of points are finite, as before. And what can we say about the count? So also for the talk, I will sometimes need a notation. So I will usually, there will be Q and Q prime, because we have two prime powers. Q will be P to the N, so the size of the field, and Q prime will be P to the M, so the, so to say, size of the Frobenius. That is just, if I need letters, Q is for the field, Q prime for the Frobenius. No, it's the other way around, of course. No, sorry. Because Q is, sorry. Yeah, and I don't, yes, I want to do it.
So Q prime is the field now, right?
FQ prime is the field, yeah.
Okay.
So, that's the object I look at. Sorry. Okay, good. Now, to be interested in point counting, so we want to estimate. So the number of points a difference variety. That's what we wanted. We replace place. In Lang-Weil we had algebraic varieties. And of course, we already had absolutely reducible, but we know, and I will talk about it later, even if it's reducible by work of Hils and McIntyre, you still have a very good understanding, even if you have formulas which involve quantifiers on the number of points. Okay, so what do we want to do? We want to estimate this, but for varying p, when two things happen. I want that the Frobenius is non-standard. What does it mean? It means p I to the mi should go to infinity. So the Frobenius goes to infinity. But also, it should not be finite index of in a bounded manner. So I don't want that ni is just mi times 2, for example, all the time. That's not interesting. So that I also want that ni divided by mi goes to infinity. So this is a regime. Yeah? The Frobenius tends to infinity, but also even the field respect. I mean, so the field degree also tends to infinity. Both.
Do you want the PIs to change, or do you
No. So it can. So this is a good question. So there are of course, there are two cases which are, like in pseudo-finite fields, drastically different. Characteristic 0 and characteristic p. If I take an ultraproduct, here characteristic p is harder. But we also do characteristic p. So if only if the p is fixed, and it depends on the choice of ultrafield. If the p's are fixed, but the m, then of course mi has to tend to infinity, and then I over mi as well. Characteristic p, because I now erased it, but the theory of value difference fields is much harder in characteristic p due to additive maps. So we have the additive operators. It was recently done by Dor and Hrushovski. It's much harder tool in characteristic p. But we will not see the difference in a little bit. Also, some twisting is necessary in characteristic p. So both is possible. So p varying as well. But also fixed possibility. Characteristic. Okay. Let me say this. Okay. Choose you an ultrafilter such that the limit when I tends to u, pi to the mi is infinity, and the limit when I tends to u, pi over mi is infinity. So that means the ultra product, okay, so setting is already true, yeah? Now we look at these guys. I take you, of course it's not principle if I have this behavior, not principle. Ultra filter on n, yeah? The actual numbers, so that I have this behavior. Good. Now K sigma will be my ultra product. So this is an infinite field with a non-standard Frobenius. The field is pseudo-finite because it's an ultraproduct of finite fields. So we know, I think so maybe, but also don't know. You know exactly what it means. Every field which is PAC has absolute Galois Z hat and is perfect, can be here. Up to elementary equivalence. This is by the famous theorem of Ax. Pseudo-finite fields. And here I have a map which comes from a Frobenius, but it's not standard. And so K is an infinite extension of fields of sigma. That's what follows from our setting.
So what have you said? Perfect.
Ultimately, yeah, so Ax, let us say Ax, yes. Such K are up to elementary equivalence determined by, so the theory Gal of K is Z hat. So it's quasi-finite field, perfect. KPAC. PAC is absolutely reducible variety, has a K point, or equivalently, every absolutely reducible plane curve. There's a point that's enough by some tricks. Igatini to reduce to curves, and then some other trick to reduce to plane curves. Okay, which is then easy to check. So it's a first order property. It's anyway a first order property, but for plane curves it's much even easier to see that it's first order. Okay, so that for the fields it's okay. The different fields are complicated, so we do not look at the full first order theory of them. We will only deal with quantifier-free formulas, which corresponds also, I mean, the varieties in Lang-Weil are also quantifier-free sets. So we are not interested in all definable sets. Quantifier-free, and at the end I will talk a little bit about existentially definable is still okay. But not more. So in this talk, such a creature, such a sigma is called a pseudo-finite difference field. Finding both properties. Both properties, yes, so these two. As I do not say it's a pseudo-finite difference field. So it's not allowed that the Frobenius is standard, for example, or the fixed series of finite index. Okay. Questions? That's the setting. Now, there is a general way of counting in pseudo-finite structures. So let's do this quickly. So if you have, in any language, an ultraproduct of finite structures, for example, a pseudo-finite difference field, so mi finite L structures, m infinite. So that means n is a pseudo-finite structure, for example, like a pseudo-finite difference field in any language. And then you can say an internal subset An internal subset is nothing but it's itself an outer product of subsets. For each of them is a subset of them. For example, if P is definable. Because the definable set is obviously the outer product of the definable sets locally. So not every internal set is definable. Well, in finite structures, but maybe it might not be uniform, so not every internal set is definable, but every definable set is internal. Good. So for an internal subset, we can define something. So we can define the coarse dimension, or let's say the normal. For example, it's definable. We define the normalized. Let me put this in brackets because I will only look at this. Coarse dimension of D. So what do I want to do? I just want to say what is the proportion. So my level is the cardinality of M. So I want to check, but I want to do it in the exponent because I think so I want to take logs. Yeah? So given by as delta of E is, I just take the limit according to U, and then you take the logarithm of the size of di divided by the logarithm of the size of mi. So if d is the whole of m to the n, it is n. If d is the whole of, if d is in one coordinate, it is 1, so it detects dimension somehow. Yeah. So this is minus infinity if the set is 0, or a real number between 0 and n. Easy. So you can also say you first compute these guys. That's what you do. This is a real number. And then you do the logarithm, and you take the outer product of it in R star, and then you take the standard path map. This is one way of computing this, for example. Because this will be a bounded number, it is between 0 and n anyway, so it lives in an outer power of the reals, but it is infinitesimally close exactly to 1, and this is the same thing as what in this here. Good. So that is the coarse dimension, and as I said, it detects dimension, of course, in normal cases. So okay. Properties. So there are other notions. Here I normalize it so that the full set gets dimension 1. Sometimes you can, if you look at smaller sets, you have to normalize it and at some level alpha. You choose a certain, maybe infinite real, and you just say, okay, this is my scale, this should be 1, and then But here we only need the normalized one, which is the scaling is with respect to the full structure. Okay, it's easy properties. What is this? That's a sanity check. The maximum, yes, and we can do the other one also, the Cartesian product. What is it for the Cartesian product? Yeah? Okay, the sum, sorry, I should not do easy things. Okay, so it behaves as it should behave. And more things, of course. Just to check that everybody is awake. But this is one notion of dimension. So what we will, and this is, if you think of Lang-Weil, this detects the exponent. We will not be able to detect the coefficient in front of q to the d. It could be 1/2 or 1 million. We will only detect the exponent. That's why we talk about this exponent. Okay, so another notion of dimension, we have another notion of dimension. So if you think of this dimension, given to a difference variety defined over a pseudo-finite difference field, you get a notion of dimension, coarse dimension of a difference variety. Now another notion of dimension in difference fields is transformal dimension. Yeah? So let's do this here. So transformal dimension is basically defined like algebraic dimension, but taking another pre-geometry, namely by transformal independence in a different field. We define it. If L sigma is a difference field, phi of x1 up to xn, a partial sigma type over L, so just a couple of formulas so that they are consistent. We set the transformal dimension, but in the theory of L, with respect to the theory of L, of pi. Now, what you would take if it were an algebra, so I take the maximum transformal transcendence degree of a solution in an overstructure, an elementary one. Maximal transformal transcendence degree of L of A sigma over L, where A is in L prime to some power, L prime sigma, which is an elementary extension of difference fields, and L prime says this is a solution. So I take a solution of the type in an elementary extension, and I take its transformal transcendence degree. Okay, here. I don't know, of n over k is the maximum number of transformally algebraic independent elements in L over K. And transformally algebraic independent means not just the elements are algebraic independent, but the elements and their iterates on the sigma. So I don't know, A1, sigma of A1, sigma squared of A1, and so on, sigma AN, sigma of AN, algebraically, in the usual sense, independent over K. So if you think for 2 seconds, how you prove Steinitz exchange for algebraically closed fields. Steinitz exchange is a consequence of Steinitz exchange for vector spaces, because You see, if y depends on x, then you can rewrite and you see, okay, vector space is finite or infinite. So you can reduce Steinitz for fields to Steinitz for vector spaces. Now Steinitz, for this notion, reduces to Steinitz for fields. Because if the last one, if there is an algebraic dependency, then it means you add not infinite but finite, and then you can invert the roles. Okay, so it's really, if you know Steinitz for fields, you get somehow quite formally Steinitz for this. So this is a pre-geometry. That's why the notion of transcendence agreement, transformal transcendence agreement makes sense. Okay, so this is another notion. Yeah.
There at the end isn't that sigma n of A1 or something?
Yeah, there is also sigma, yeah, so it continues forever. And then there is an, I mean, I have a tuple. I have a tuple. If they are algebraically independent over K, then, but if and only if, A1 up to AN, by definition, is transformally algebraically independent over K.
Yeah.
So I have to check A1, sigma of A1, sigma square of A1, blah, blah, blah. A2, sigma of A2, sigma square of A2, blah, 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 blah. AN, sigma of N, blah, blah, blah. You're just not happy with the number of indices I wrote. But okay. The elements and all the iterates are algebraically independent. Good. So okay, if K sigma is as before a pseudo-finite difference field, pi of x is over K, set delta, so the coarse dimension of pi, I will define it as the infimum of the coarse dimensions of the formulas in the type. I define what the phi of K. So you take any definable set implied by pi, and so this is just, you take a definable neighborhood of pi and you measure its coarse dimension, take the infimum. So this is nothing to experience. And the theorem is, this is the same. So this is theorem 1. These two notions are the same. So theorem A. These two are the same. So let K sigma be a pseudo-finite difference field in the regime I talked about. So Frobenius goes to infinity and the type of the field goes faster to infinity. Pi, a quantifier-free partial type. For example, a difference variety is a special case. It's just defined a set. Partial type is an intersection of varieties. Partial type over K, e.g. a difference variety. Case when it's definable. Okay, then the two notions are the same. Which means the exponent in the count, if you think of a count, is detected by transformal dimension. In finite fields, assuming finite fields, it is the Zariski dimension which is detected by the count. Because if you take the rational points, you take the Zariski closure, and so in Lang-Weil, even if the variety is not absolutely reducible, still the maximal transcendence degree of a solution in pseudo-finite setting of a solution will be equal to the d you get in the count. So that is.
Sorry?
Yes.
Is it an obvious majoration between both and then the theorem?
One is obvious.
The other one?
So one is obvious, yes. So you cannot have more points. So you need to show that there are many points. The other direction is easy. Yeah, the other direction is easy. So you get an upper bound easily from Lang-Weil. Okay. Very easily. Because you can count the number of components you get when you specialize is polynomial in.
So delta is bounded by the transformal dimension.
Yeah, so that exactly, this is clear.
Okay.
It's elementary. Exactly. Yes. This is elementary. So the whole point is how to find many points. And then in the controlled way is then also not so good. The point is how do we get access to I mean, we want to use Lang-Weil and we need to do something. Okay? So that's, in particular, let me say in particular, in the special situation, if pi is over a countable subset, first of all, which is not at all clear a priori, this is always a natural number. Was not clear before. Will be equal to this, okay? It's a natural number. And if pi only uses parameters from a countable subset, for example, if it's just a variety, then I can even count the maximum inside K. Then delta of pi is equal to the maximum of transformal transcendence degree of A over A.
Is this the fact that the thing is going to be at quantifier-free?
Yeah, exactly. But there's not exactly, there's only this. A in pi of K. Yeah, as Adrian said, because every type over A is realized in K because K is Aleph 1 factorial. So this is somehow a joke for those who know. But of course, in this pseudo-finite setting, because the index set is countable and the algebra is non-principal, we always get Aleph 1 saturation for free, and then we get this. So we can also count inside. Okay. Good. Now a remark. I said it before. So the measure, the measure by Chatzitakis-Mann and Rees-McIntyre in pseudo-finite fields what follows from their work? So very, very generally, if phi of xy is an L ring formula, it can have arbitrary quantifiers. There is a finite set of pairs, measure, or dimension multiplicity, I should say, contained in. So I have on the left-hand side for the dimension, I have something between 0 and the cardinality of x. Number of variables. Y is there to plug in a parameter. And on the right-hand side, I have a positive rational number. I may also have 0, 0. It's a finite set such that in every finite field you get a count. In every FQ, and potential parameter for the formula, so in the length of y, there is a d mu, this is finite set. Finite set d of phi contained in, there is a d mu in d phi, so one of the finitely many options, such that you have the count. Number of solutions of phi with parameters b minus multiplicity times q to the d is bounded by q to the d minus, constant, there's also a constant. There's also a constant. There is a constant c of phi and a finite set such that. What does this tell us? It tells us, if you think of coarse dimension, we can't see the mu. We can only see the d. Yeah? And so for example, in this count, we could be 1 million times q to the d. Problem is, for example, sigma of x is equal to x. Think of that. It has transformal dimension 0. But you count the number of solutions, it is q. So you can't avoid that before you have a polynomial in q. But q, not q prime, q. So the medium size thing. So to continue with this result, which is quantifier reduction. So in pseudo-finite fields, arbitrary formulas are Boolean combination of bounded existential, and even if you add some constants for the coefficients of irreducible polynomials of a certain degree, you get even, every formula is given by a projection of a variety with finite fibers. And then you count, and then you get the mu because it can be 1/2 for the squares. For example, it can be 1/2. There is a y squared is equal to x, that has roughly half of q manifolds. Okay, good. So if q is large enough, note that of course, at the beginning for small q you can have several d mu that work, but then from a certain point on, the growth rates are such that there is only one case. These cases are exclusive. And so in the pseudo-finite setting, we get exactly one. Because I didn't say, but there's also the cases are definable. This is underlined. I don't think. Yeah, you get exactly one case. The D in question is then the cost division. Just to relate this result to our discussion here. So the D we detect, the mu we don't know. Later. Okay. And also note that what do we have? Delta of phi of f, as a pseudo-finite field, is equal to the dimension of phi of f, which is equal to the algebraic dimension of the Zariski closure of the rational points. So there it's also, to relate to this result, the transcendence degree detects, in pseudo-finite fields, it's also the transcendence is equal to this coarse dimension. But the transcendence degree, not of the variety, but of the variety when you take the closure of the rational points, you may get down. If your components are not defined over f, then this might be much smaller than the initial variety you had. Okay. Other questions? I'll continue. Okay, so the idea is we just want to use Lang-Weil. It doesn't look so complicated. We want to use Lang-Weil to prove the result. So I said that we need a little bit of difference algebraic geometry. If I have a difference field, x in a to the n, a difference variety defined over L, so just given by a finite conjunction of different polynomial equations. So zero set, or the zero set of finite remaining P1 up to P, I don't know, M in L x sigma, many. Then, okay, X, I should say, this defines the topology, and it is Noetherian. It's like in differential fields, you know. Cauchy topology in differential fields, this is cone, Zariski cone topology, it's also Noetherian. So you have the reducible decomposition as you are used to. Just at the level of ideals, it's not Noetherian, it's only Noetherian at the level of radical difference ideals. So you, if you know the differential case, it's very similar. So if x is irreducible, we transform the dimension of x, so no index here, as the transformal degree of the function field in the right category. So L of x sigma over L, where of course L of x sigma is what you suppose, where L of x sigma is just the fraction field of L of x sigma divided by I, where I is then the vanishing error, where I is the difference prime ideal defining x. X is irreducible, so that means it is defined by a difference prime ideal. So the quotient is domain, together with sigma, which is injective. And so you can take the fraction field into different. And this one is not inversive, that's what I wanted to say. This one is not inversive, I don't need it finally generated. So it's of course the same thing as in algebraic geometry. A generic point, a bar of x is the same. If you take the field generated by the different field, it's exactly the same thing as this function field. Like, happens the same way. Okay. So now we want to specialize. So we need to leave a little bit the work. I mean, usually in monosphere we only want to work with different spheres and we don't like different domains. But here we need to do this a little bit. So say if you have a finitely generated different subdomain, so just as a different subdomain finitely generated, such that all the PIs have coefficients in X and in D, okay, good. Then eta from D sigma to some D sigma difference ring homomorphism with B sigma a difference domain. So I only look at difference domains, which means my sigmas are always injective. So not only it's an integral domain, but it's also the sigma is injective, so it embeds into a different field, namely the fraction field is automatically a different field. I don't want non-injective morphisms on domains. So I have such a map called specialization, and then I define x eta is just what you think, so defined by you want eta 0 is Pn. And these guys are, of course, just obtained by replacing the coefficients by their map, by their image under eta. So it's a base change, yeah? Base change via the map from B sigma to B sigma. Okay. So claim. So we need some uniformity. Localizing. So there is D in D prime in the field of fractions of D. D prime finitely generated difference domain. So I only have to invert finitely many elements from D, such that I guarantee that for all eta now defined on D prime, so if I inverted certain elements, you see the transformal dimension of the image is bounded by the transformal dimension. This is easy. Because you just say that certain things are non-zero. So you have to invert certain things, and it's like, okay. Okay. Now notation. LQ will be FQ alg together with Frobenius Q for Q a prime power, algebraically closed, and Y a difference variety over LQ, difference variety over LQ. In LQ, I can replace sigma by x goes to x to the q. Is obtained Frobenius specialization. Obtained by replacing sigma to the m of x by xi, say by xi to the q to the m. That's what you do. So I replace sigma by Frobenius in my variable. So of course that means in LQ I get the same points. So MQ of y in algebraic variety and MQ of y of LQ is of course, because on this it does the same thing. It's y of LQ. But you interpret it in an extension, it gets different because here the sigma has to be Frobenius. So if I want to count points, I may of course as well count them in the algebraic variety. Main problem 4. So main problem. want to control the local dimension of the components, of the irreducible components of nq of y. The problem is nq of y has unbounded degree if q varies. So it also has unboundedly many irreducible components, so you can't do it with the normal formula from algebraic geometry. You just can't. Doesn't work. So and the problem is, we want to use Lang-Weil. Okay, let me do a picture. We want to use Lang-Weil. Suppose we find a point. We find a point. The only thing we will be able to say is that the rank of the Jacobian. This will be something which passes under specialization. So maybe I know that here this looks like a smooth point because if it were on a component of full dimension, it would be smooth, but it's not. So I would like to know that this is not on a component of full dimension. But I can't talk about the components because there are too many. So in algebraic geometry, there is a uniform way in a family of talking about the components. Here I can't. So we need to somehow find a way to get access locally to dimension, which we cannot do in the Zariski-Krohn world, but which we can do in value trees. If we had a valuation, you can say around this point, the dimension is d. Right? So if we had a strong topology, we would be happy. And that's what we do. So this is the main problem is, we want to use Lang-Weil, so we need to know that we lie on a component of maximal dimension, which will then, if it's a smooth point, the component, a rational point on a smooth rational point on a component can only lie on one component, and the component is defined over the same field. So that is the way to go, and then we can use Lang-Weil. The only problem will be to control locally the dimension so that we know on what component we are. So this is your theorem, and this is what we actually prove. Okay, so this is what we actually prove. It's like a purity statement. Let x in n be a difference variety of transformal dimension d over a finitely generated difference domain. So it's a quite uniform statement. You can think of this, it's a bit like it's like parametrizing line. It's more a bit of a schematic way of parametrizing, yes?
So there is an eta, and eta gives also a kind of endomorphism, or what is it?
No, it's just a homomorphism.
Homomorphism.
Sigma homomorphism. So it can kill people.
Okay.
But the codomain is also a difference domain. So it's also an integral domain with an injective homomorphism. But the map need not be. For example, Z with the identity goes to FP with the identity is perfect. For example. Yeah? You look skeptical. No. Okay. Good. So finitely generated blah. Then what? Then there is a different subscheme. Different subvariety. Those things here. XS in X, defined over D as well, of transformal dimension strictly smaller, a small thing that I have to take away, and D in D prime in the, so I have to invert finitely many elements, or one element, D prime finitely generated, difference domain, such that I have to have a very good control. 1. For all q large enough, and eta going from D prime sigma to LQ, LQ is, LQ is LQ, Frobenius Q. Yeah? So I have a map which is a homomorphism from D prime to FQIH, and sigma is converted to the Q Frobenius. The algebraic dimension, sorry, the algebraic dimension of MQ of XS eta, so the thing I get when I think of it as an algebraic variety, is smaller than D, so that's fine. It's also small, so the count of the rational points does not matter later. And this is the main point, what we have in the rest is equidimensional. Dimension D. Or empty. Could be empty. For certain specializations. So, but if it could happen that in the specialization your dimension drops, but then everything is eaten by XS. See, now the problem disappears. This cannot happen if I took away. I can before I specialize take away enough things so that I can never run into this problem in X minus XS. And then we are home. Okay. This is 1. I mean 2 is now count. The count is. So assume you have a non-empty open different subvariety, also defined over D. Then there are constants, little c and capital C, only depending on x and u, such that for all q, p to the m larger than c, so large enough, for all eta from d prime to LQ, for all t in n bigger than 0, such that the specialization lands in fp to the t, could happen. In particular, if n divides t and it lands there. If mq of u without xs eta of fp to the t, I don't need an automorphism anymore, this is an algebraic variety, is not empty. There are two cases, either it's not empty, then I have many points. Then now what Antoine asked, then I have many points, then I have the set of points of fp to the t. But note this is equal to u minus xs evaluated in fp to the t for q, of course, it's the same thing. Is bigger or equal to what I wanted, so it was, did I say transformal dimension? I said, yeah, d was a transformal dimension, so it's at least p to the dt, which means p to the t to the d, so that's what it should be, minus something small, q. Remember, q is much smaller. Q to the c, the polynomial in c, p to the d minus 1, half times d. So if you think of p to the t is q prime, then it is exactly what we wanted. Okay? But it even works for smaller t, but then it's not interesting. We want to have it for large t. Okay, if it's not empty. And if it's empty, else it's eaten up by xs, of course. Else, let me write it with else. Let me write it like this: x minus xs of fp t for q is entirely x u minus xs is entirely contained, of course, in xs eta of fpt or Q thus of cardinality, of small cardinality, at most Q to the C, P to the D times T minus 1. Other way around. T times T minus 1. Okay, so that is the result. Two cases. So, no, the important thing is there is an a priori way, or before specializing, uniformly we take away some different subvariety of smaller dimension, so that what remains, you can no longer specialize in a way that you get a component which is not of maximal dimension. It can be empty or not. If it's not empty, you have many points. So that's the result. And you can of course imagine that the first result follows from this. So I will only only test the proof of the second, and the first is somehow using this. So I said the upper bound is easy to establish, so that's why the coarse dimension is settled. Once I can show it's at least D, and which will follow from this count here. It's at least D. Other questions? Statement. But it's only a very rough count. Okay. So now, the last 20 minutes.
So for the count in item 2,
Yes.
sorry, is it important to subtract the set xs?
No, not at all.
Okay.
The point is, here I don't know if I cannot express it here. The only point is if it's not empty. So here I need to say, if I have a point in the region, because this just detects, is it empty or not? It can be empty. If it's not empty, then I have, of course, if it's not empty, the point is not clear, but I will find smooth points in a version of it. Not in this one, but we will twist. Maybe our variety, if we specialize, the derivatives are always zero because the because they are stupidly used. Then we will replace. So then we replace sigma by tau, which is sigma Frobenius to the -1 finitely many times, and this will not affect the count, and work with some other version of this problem somehow. So we can guarantee that we find smooth points, and then good. That's also, as we said, yeah. For this count, I can forget this, of course. Yeah, maybe I should even. Because the upper bound I have it anyway, so I can forget about this part, but I need that this is not empty. Yes? Yes, no. Okay. So I would say 2 follows form 1, and strong Lang-Weil if we know that there is a component defined over F Q prime, then we are home. Absolutely beautiful component. But actually XS is set up so that we may stratify X without XS into locally closed as, I don't know, X0 X I open in X without the previous ones, right? Open, such that, and I want to be vague, such that Xi of F, Yi of F, for any, even with an eta, for any perfect inversive difference field. And this one-to-one correspondence is given by not just a rational map, but I also am allowed to invert P, Frobenius, and I'm also allowed to invert sigma. Perfect inversive, such maps are bijections.
Perfect is pure theoretical.
Yes, theoretically perfect and inversive. So what we do is, this allows us, so on each of these things, to work with tau, which is equal to sigma composed with Frobenius to some Frobenius P to some minus K, K in N. I have to take plus K, minus K. Minus K, yeah? In the world of perfect difference fields, it doesn't matter so much. I can describe the same set with polynomials over tau. Because I can also take roots of coefficients, with roots. So I can describe the same definable set. This is one thing. So I can change it so that I find, and also using the primitive element theorem for difference fields, there is one such. You may assume that E is n minus 1. So X is of codimension 1. See, I can find a generating a tuple for the difference field, for the difference fraction field, which is of a cardinality, like in algebraic geometry, cardinality E plus 1. The problem is, it doesn't mean that it's a hypersurface with a single equation, because this is not true in difference fields. So in algebraic geometry, we have Krull Hauptidealsatz. Here we don't. So maybe more than one equation needed. But of course, once you specialize, you only need one equation. After specialization, okay, you could rewrite. But so what we do is, and then using this twisting and codimension 1, find a polynomial q, say q0. So I do the first step. You do it. You work locally on the generic point. You do something on the generic point. You will find the x0 by just extending. You find q0 in p of x sigma non-zero, such that q0 on x0 vanishes to 0, even on x, but dx1 q0 is non-zero on x0. So what is this derivative? I only derive with respect to x1, so all the iterates of sigma for all variables for all j, for all n bigger or equal to 1. So I really take, so the sigma of x are treated as constants. They are Frobenius or something. So they should be constant. X to the p, x to the q, they should have derivative 0 because it has after specialization. So I need to take this definition. So, but you can imagine, you have a certain equation, maybe it's not good because the derivative is 0. But then you do this move with the tau and you replace a little bit. But this is done uniformly, so you do this finitely many times, so you only invert Frobenius finitely many times, so the constants get worse, but at the infinity it doesn't matter. Okay? So this is a bit vague. So there is some preparation. And now I know that whatever point I find after specialization, it will be smooth. So the components will be smooth. I guaranteed it by this business. And so if I have a point, I have a smooth point, and then I get this. So the components, the absolute irreducible component of a rational point, which is smooth by the Jacobian criterion, is defined over FQ prime. So Lang-Weil applies. At the international point, the conjugates would also contain the same, so it would lie on two components, but the Jacobian process is smooth, so it's not possible. So Lang-Weil applies. So the only problem is, how do we prove part one? So this actually, I would say, this is maybe the really interesting theorem of our paper is this purity statement, because the rest is just some yoga with the constants from Lang-Weil and this is, I mean, this is all elementary. It's very, it's not nice to write up this twisting of the math. But so this is the, I think this is the interesting statement. And maybe so I don't know. The different algebraic geometry is of course not so developed, but maybe one can prove this not with model. So we prove this is model theory. And it looks like, I don't know. So purity statements generically, it's, so the rest of the talk, which is 10 minutes, I want to spend on ideas how we prove this. Part one, yeah? I can actually erase this, because I just keep part one. This board. So, okay, now, how do we do this? So there is, so as I said, want to use the strong topology evaluations. Because this is locally, you can say locally things about the dimension, like in minimality. You can talk about local dimension, which you cannot do in the Zariski or Zariski-Kronburg. So with topology we can. So what do we do? So we look at LQ tilde, which is LQ of t. Okay, it's just LQ of t, but LQ was FQ alge, yeah? The alge, chaotic valuation, or an extension of the chaotic valuation to this guy, and Frobenius to the Q. Value difference field. And now let's take VFA tilde, the limit theory. A set of sentences in the language of value difference fields. So you have both the valuation. For example, you can name the O with the predicate, and you have the isomorphism with the sigma. So all the sentences such that LQ tilde holds for phi for all Q large enough. And this is the limit theory. I can define it. Limit theory. Like in Axe's work, the limit theory of all finite fields, Axe showed this is the theory of pseudo-finite fields. So this is the limit theory for these creatures. And so, theorem. So, Dor characteristic 0. Because you have to analyze two situations when Q is the same prime and when it's the power of the same prime or not. Characteristic 0, 0. Dor and Hrushovski, much harder. Arbitrary characteristic. Behind it lies Moody's non-standard Frobenius result anyway. So this is already behind without valuation. So what do we have? VFA tilde. So VFA tilde is a model companion of the theory VFA of valued fields with contracting automorphism. Contracting means if V of x is positive, then V of sigma of x is bigger or equal to n times V of x for all elements. So it shrinks the metric. For small elements get much smaller. Another Archimedean. Of course, it's true because it's locally true almost everywhere. Given an n, if q is larger than n, it's true because q acts, Frobenius acts like multiplication by q on the value group. So that's one thing. But it's a model companion. That means these are exactly the existentially closed models. No, I mean up to elementary equivalence. They're existentially closed. Okay. So we can, whatever problem we have, we can think of this. Everything embeds there. So this is the generic case. 2. If L, KL is the residual field, gamma L is the value group, sigma is a model of VFA tilde, then first, little kl together with the induced automorphism, you get an induced map because sigma respects O, is a model of ACFA. So it's an exponentially closed. This is by Hrushovski's result on Frobenius. And it is purely stably embedded. What does this mean? This means whatever I can define in the whole structure, L gamma k, but in the residue field, so using the evaluation I can say there is an element, there is a polynomial, such that this is evaluation complicated things, and I'm the residue of these, for example. You can also define it just with sigma bar on the residue field. So it's purely stable, like in ACDF, there you know it, residue field is a pure algebraical field, it's a pure difference field. So what we will do, we will find the XS by a definition which employs valuation and on the big field, but XS will live in the small field, and then we have it. This is 2 and 3. This is also more difficult than you think. Actually, very difficult. I also tried to prove this for, I don't know, very long time. Failed miserably. So if type of type P of X, PO of X. So you know in ACVF there's a generic type of O, unique generic type. I'm in O but not in any proper subball. Of an element of O such that the residue of X is sigma transcendental. So this residue type is well known in ACFA. This is a complete definable type. By you use some result of David actually of this. So this is a complete type. And if it's complete, it's already definable because I wrote the defining scheme. It's a complete definable type. That's good. So that means I can talk about a generic tuple in O to the D. And it doesn't, I mean, if something, okay. And now what we do is, now let me just briefly say what we do. So we take KL, sigma, yeah, and here is OL, sigma bar. But we can also find the lift. This is clear in the ultraproduct here, of course. The ultraproduct of the LQ lies just as a sublet. You can always find a lift. As in Henselian valued fields, the residue field always lifts. It's also true in sigma Henselian and the different fields. You can always lift by Hensel's lemma. I can find this lift. So I can look at my x of KL, but I also have x of L and in particular x of OL, if you want. I have a map here. Right? And what you can say is, you can now just suppose, there's one thing I forgot. 2 minutes, so I will just say it. The topological dimension in VFA, tilde, of a definable set defined just with difference polynomials, is the same as the transformal dimension. Like in ACVF, the algebraic dimension is the same as the topological dimension. So the largest D, so that you can project onto D many variables, so you have a non-empty interior in the evaluation topology. The same is true in VFA. So in order to detect Sari's cone dimension, the transformal dimension, I may as well detect topological dimension. And then I can, so what I just do is I say, so there's also a D in the framework, and I take some point, and I check that, so take a generic type, then O to the D, which is hit. In the fiber you find a ball, because they all have the same type. They have the same type, so if one is in, the others are also in. You see? And so being of dimension D, you can just say, okay, my rest to the minus one of myself contains a full ball. Okay, so the topological dimension is definable locally. And there is implicit functional theorem behind. I mean, the fact that you can lift such things is okay. Prove something. And so using this 3 uses that it's definable because I can just say, I know that if someone is hit, then if someone has this property that there is a ball, then since it's a generic type, all the others close by will also have this property, so that there will be a full ball. Okay, don't give the precise thing, but with these two, you can make it. So you find a definition using 3, but then you realize actually what I had to say lives in the residue field, and so it can be set only with difference algebraic condition. And then you realize that you can do it quantifier freely. And so, in the end of the day, it's like you find a constructible set you have to take away, but generically it was true, so that's why you find a set of small dimension. Take it away, and then you're done. Okay, thank you.
Questions? At the end you said quantifier freely, but why is that you can take it quantifier freely?
Okay, I can, okay, a priori, you see ACFA is not so bad. So the set will anyway be a Boolean combination of bounded existential. We define it as set. But then you can, X is a quantifier free, X is a variety, yeah? But, so X, I can just, okay. I don't know what to say. Okay. Taking away some definable set of smaller dimension, then I can take the Zariski cone closure and take that away. And that will then be quantifier free definable. So it's a bit like, if you take away a constructible set, you know the dimension is smaller, you can also take the Zariski closure. But here it even works if you have quantifiers. So you just, the important thing is what I take away first is of smaller transformal dimension. But then it's and then there is a closure by neutrality, so the Zariski cone closure is also of smaller dimension, you take that away. Yeah. So that's, yeah, normally, yeah.
Yeah, there's this side question I received from Borovik. That's Borovik's question. Could there be a Lang-Weil estimate for difference fields of finite Morley wrong?
Oh. Problem is, what are the difference fields of finite Morley ring?
Yeah, okay. So supposing that there are, bizarre ones, like entire ones.
I mean, they will not at all be pseudo-finite. They will be the contrary, of course. They will not come from finite fields, so I don't know at all, because you don't even know, it's not even pseudo-finite, you don't know what to give as a coarse dimension. You can't count points because it's not pseudo-finite.
No.
So you would have to do something else, right?
As a dimension, they have Morley wrong, I guess. But,
Yeah, sorry. They have Morley rank. Yeah, but they have Morley rank, yes, but what is the second dimension? Because I need a delta, right? And you have Morley rank, which would correspond to transformal dimension, but I would need another one. No, if you look at the fixed, okay, I don't know. I can't really make sense of the delta, you see, because that's so. But I think the techniques would not. I mean, in some sense, as I said, the moral of the story is there is Lang-Weil, there are good bounds, you can convert. There's only one problem: how can I guarantee equidimensionality? Because you turn in circles. If you find a point which has maximal Jacobian rank, but you don't know it lives on a high dimensional component. If you knew that, you would be done. And so we tried for a long time using Plantini, but I mean difference Plantini, but somehow nothing worked. And okay, then Udi came with this idea, which of course solved the thing very nicely. So I think this is if you want, there is one take-home message is this one, and then.
I have one more question. Maybe it's too long to explain, and then you do it over lunch. But is it easy to compare with the older work that Udi did on Lang-Weil estimates for?
It's much easier. No.
Now there are approaches. This approach is.
This is soft. This is soft modulo this result, but this uses, of course. So in some sense, it turns this one uses. I mean, I don't know. I don't think you can prove any version of this without knowing his non-standard Frobenius result. So you inject it here, but what we add on it is it's infinitely softer compared to what, because as I said, this is the only. And also, even this is soft modulo. So in some sense, we just put together pieces. Yeah, the stratification, but this is an elementary procedure to do this. So, yeah, no, there's no, it doesn't compare. I mean, okay, I didn't say, it also goes to existential, but it does not go to more complicated definers. So there's a counterexample due to Michael Benedict and Dor and Hrushovski. the image of 1 over x minus y. Y is a transcendental element, x is from the fixed field. This is an FP linearly independent set, and for some strange reason, the linear hull is definable. FP linear hull of this infinite set, and you can take this as it gives a counterexample, but it needs this definition needs some quantifiers. So it's not for extension sets it's still true, but it doesn't go more generally. But this I would say this is another. The geometry is soft, apart from this. So it's all you manipulate function fields and you extend a little bit and you stratify. It's not more than one.
Questions or comments? If not, let's thank the speaker again.